Hello, thank you everyone for coming. We really appreciate you taking the time out on a busy Sunday evening to come by and listen to us chat to you for a little while. And we hope that this will be very interactive because we really want feedback and have a discussion. My name is Gary Ahn. I'm one of the co-authors of this book, Translational Systems Biology. I'm a trauma surgeon by training, computational biologist by hobby, and now kind of professionally. It's my colleague Yoram Vodovotz.
Hi, I'm Yoram Vodovotz. I'm a scientist by profession and a computational biologist by evolutionary pressures. And I ended up with Gary approximately 10-12 years ago, starting down this path of thinking about how to do computational models of inflammation in very major public health problems such as sepsis, trauma, wound healing, and related phenomena.
So we're going to start by just doing a little intro reading from the book, introduction. Okay. You guys can hear me though, can't you? Yeah. Do I need to?
Oh, no, not.
I don't want to.
Yeah.
Whatever. All right, so the first words obviously are not ours, but I'll appropriately attribute them. So it was the best of times, it was the worst of times. It was the age of wisdom, it was the age of foolishness. It was the epoch of belief. It was the epoch of incredulity. It was a season of light. It was a season of darkness. It was a spring of hope. It was the winter of despair. Obviously, Charles Dickens, Tale of Two Cities. Well, we want you to consider the following scenarios. You're driving home from a party, and a drunk driver runs a red light, striking your car from the side, crushing the door and trapping you inside. The paramedics and firemen arrive quickly and cut you out, but you've lost a lot of blood and are in shock. They get you to the hospital where you were found to have a broken leg, a broken pelvis, a collapsed and bruised lung, and are bleeding internally. You get a series of operations to stop the bleeding and fix the fractures, but you end up in the intensive care unit on a ventilator because your lungs were too badly damaged. Next scenario. You're recovering from a cycle of chemotherapy for your breast cancer, and your doctors are saying that you appear to be responding well. But a few days afterward, you start having fevers and feeling very poorly. You call 911, and by the time the paramedics can get you to the hospital, you have a very low blood pressure and are having trouble breathing. The emergency room doctors diagnose you with bacterial sepsis, and because you are immunosuppressed from your chemotherapy. They start intravenous fluids and antibiotics and transfer you to the intensive care unit. Another scenario. It's flu season. Despite being careful, you start coughing up greenish-yellow phlegm and are sweating at night and having chills. Your family brings you to the hospital where they say you have pneumonia. You are admitted and placed on antibiotics, but over the next day your breathing becomes more difficult, your blood pressure becomes a little low, and they transfer you to the intensive care unit and tell you they need to put you on the ventilator. Another scenario. This one actually affects me. You've been shoveling snow and developed really bad chest pain. You call 911. Paramedics take you to the emergency room where they diagnose you with a heart attack from occlusions in your heart's arteries. Based on where the blockage is, you need to have emergency heart bypass surgery. The operation goes fine, but afterwards your kidneys no longer work, and the wound in your leg where they took the vein graft is looking red and maybe infected. About 5 days later, you have difficulty breathing. They put you in the ICU and tell you that they need dialysis. There's another scenario. You skin your knee playing basketball at school. At first everything seems fine, but after a couple of days you notice that it's getting red and more swollen. The redness starts creeping up your leg, you start having fevers and chills, you feel dizzy and lightheaded. You go to the doctor who diagnoses you with an infection of the flesh-eating bacteria. She tells you that you need to be admitted to the hospital immediately. By the time you get there, you're in shock from the infection, you have to go to the operating room emergently, and you will end up spending a lot of time in the ICU. Last scenario, I think. You're recovering from your broken hip, but because of the pain, you've not been getting out of bed very much. Your cough is worsening over the past couple of days, and despite trying to cough out the phlegm, you're having more trouble breathing. You get some fevers, the doctors diagnose you with pneumonia, start you on antibiotics. However, despite this treatment, a few days later, your breathing gets more difficult. They need to put you on a ventilator and transfer you to the ICU.
So most of us don't spend much time thinking about acute inflammation or critical illness, how it gets. But hopefully from these scenarios you got a sense for how common these events are. Maybe we should. So, regardless of the disease that scares you most, or of what statistics say people die from, in this day and age, the final common pathway is nearly invariant. An encounter with the healthcare system, and if you're sick enough, care in an intensive care unit where you will be the beneficiary of the best life-saving technology that can be provided, at least as long as you live in a developed country. The disease process that puts you there, however, nearly always stems from the same source, regardless of what started it, your body's inflammatory response to some initial insult that, if it becomes disordered, can lead to the rapid progressive failure of multiple organs. Depending on myriad factors, you could either find yourself spending a lot of time in the hospital, after which time you may need further convalescence, or you could die. This is something of an ugly little secret, swept under the rug, lost in the shuffle, as doctors and biomedical researchers focus on the individual diseases that drive toward this final common pathway. So why has a highly developed society like ours not yet solved the puzzle of critical illness? We lay the blame squarely on the current state of biomedical research. Biomedical research today lives in a world that, in many ways, is strikingly similar to that of the French Revolution as described by Charles Dickens in the initial quote that Gary read. It is a time of incredible promise, resulting from unprecedented advances in technology that has led to a previously inconceivable degree of characterization of biological systems. The window into the essential components and machinery of life has never been so wide, and the resulting view so sharply defined. However, as this embarrassment of riches carries with it a wealth of expectations, so too is there a corresponding chasm of disappointment when those expectations are not met. How can this increased ability to peer into the workings of biological systems be translated into actionable knowledge that can be used to aid mankind? This is the translational dilemma that faces biomedical research, the ability to effectively translate basic mechanistic knowledge into clinically effective therapeutics, most apparent in attempts to understand and modulate so-called systems processes and disorders such as sepsis, cancer, and wound healing. Unfortunately, the translational dilemma appears to be cropping up more and more often as, paradoxically, a greater understanding of the processes that lead to the transition from health are known, the more intractable trying to manipulate those processes seems to become. Thus, the current situation calls for a reassessment of the scientific process as an initial step towards identifying where and how the process can be augmented by technology. The U.S. Food and Drug Administration report, Innovation or Stagnation, Challenge and Opportunity on the Critical Path to New Medical Products, also known as the Critical Path document, clearly delineates the steadily increasing expenditures on research and development, concurrent with a progressive decrease in delivery of medical products to the market. In many ways, the biomedical community can be viewed as standing on the ledge of in a canyon, able to see the upper rim above, but faced with no path in that direction, and at the same time fearing the depths that lie below. So, but what makes what we do different is, so there's, especially in this town, a lot of work, people in systems biology, computational work. So what makes what we do different? So what's the message of this book that just isn't, hey, do computational stuff? So the number one different aspect of the message is start from the clinical reality. So here's another sort of dirty little secret about how grants are written or papers are written. You know, I like to study cells, so I'm going to tell you that it's really all about cancer. So you go, okay, cancer. Yeah, well, you know, it's got cancer cells, right? And, you know, it's tough to study cancer cells in an actual patient because, you know, they're all kind of different. They end up with different outcomes and stuff. So what I'm going to do is I'm going to get cells from a patient. And, you know, it's hard to get cells from a patient. So what I'm going to do is I'm going to get cells from a patient and then grow them for a long time in the lab. I'm going to ignore the fact that actually this thing's acquiring mutations like crazy, just growing in my incubator. But I'm going to study it because, you know, it's a lot easier to look for your keys under the light than it is to look for your keys in a very dark street, especially a dangerous neighborhood. So now all of a sudden you go, oh, but you know, but it's about cancer. You know, I mean, it's true I'm working in cells. Now the thing is, if I do computational biology on those same cells, I'm still just working on those cells. Right? I can tell myself that it's cancer, but honestly, it could just as well be 10 million cycles of mutation in an incubator that I'm studying. And that's another part of the process that I think really differentiates what we do. Our first work was focused on where the clinical problems were. Where the clinical problems were was the inability to take drugs that companies spent, say, 15 years developing and get a clinical trial that works. So they go, we had all the evidence in studies in cells and in animals and in phase 1 trials in people and in phase 2 trials in people, and we had a feeling that this should work. And we spent $50 million on a trial, and we went to a phase 3 and it failed. And in the sepsis field, that only happened about 300 times. So, scientists are pretty good. They're only going to, you're going to take about 300 times and several $1 billion of spending before you go, let's just do that again next week. Right? And actually, this happens across the board. I mean, you could argue that successful trials are so few nowadays, and that's that critical path document that I mentioned. So what we said was, there's 2 ways you could approach this. You could come from, let's simulate 1 billion different cell cultures and hope that someday that'll be a virtual human. Or let's just start getting data from people. Let's just start simulating the problem where it really is, which is the clinical trial didn't work for the drug you already have. Okay, once you get that, then maybe you take a step back and you go, well, if I can do a pretty good job of that and convince myself that this can work for a population, I could still be wrong. Like Gary said, we want to falsify our hypothesis. I could still be wrong because I could get it right for the group, but I could be wrong if I looked at any one individual. So the next part is take that same model, get data in people that you can get that are variables that are in that model. So not every piece of data, just the parts that the model says you need. Make patient-specific models. And then when you've got that, then you could maybe go one step further back and say, well, that's what we did when we tested it out for a drug we already had. But who said that that drug was the best drug we could have made? Because honestly, if you knew anything about drug design, it is very, very far from an optimized process. We can have that discussion if people want. So the bottom line is drugs make it to be a drug through a combination of science, rationality, politics, money, and and coincidence. And then that's what makes it, after 15 years and about $2 to $4 billion, to be a thing you can give to patients in a trial. Right? So wouldn't it be better if you could say, hey, I believed a simulated trial, I believe patient-specific models, maybe I should use all that to make new drugs. I should just make a drug that will change the simulated outcomes. Right? I should come up with what the properties of the drug should be. Because I believe them because they would work, right? The model that I'm using to do it in is a model that has already proven itself up until this point. So now if you did all that, all of a sudden you just discovered a rational pathway to go from the basic mechanisms people believe in to a drug that will work in patients in a trial. And that's translational systems biology.
Because that first step where you use cultured cancer cells and you do reductionist experiments, you have to do that, right? Because that's how mechanistic science works, right? By the very nature of how you do experimental science to identify what those mechanisms are, you have to do experiments that way, right? That's a fixed constraint. So the question is not how you do those experiments or how you can do them differently, but what do you do with the output of that experiment? So right now what we do is we make a series of cognitive leaps, huge assumptions, based on what the overall aggregate system looks like, based on what we think the individual components actually are. And we know that the complexity of biological systems allows us not to necessarily make that inference. So this is when I give my regular talk. Here's an example that I use. So I do a thing called agent-based modeling, which is basically looking at systems as groups of interacting components that are acting on a series of rules, and they basically act with their neighbors. Most people interact with agent-based models by going to the movies or in video games. So if you've gone to like the Lord of the Rings movies or World War Z, etc., these big crowd scenes, those are agent-based models, right? Where each individual creature is a computer program sitting on a grid. So when they made the first CGIs for the Lord of the Rings movies, they programmed what they thought were very reasonable stand-and-fight rules for the orcs and the elves, right, in the battles. And imagine they're living on a big checkerboard, and the rules are like, if I have X number of my buddies with me, I'm going to attack, and if I have Y number of people in front of me, they're enemies, I'll run away, all right, and basically results in these very realistic sort of things. But when they started doing the simulations to do the CGI, the armies would come together, and they would touch, and then they would run away, right? Because there are population effects that cannot necessarily be inferred based just on how the behavior of individual components are, right? And cells are exactly like that. Anyone who's done any cellular biology, you have a set of clonal cells You apply one particular perturbation to the entire dish, and you look at it under the microscope, and half the cells did one thing, and half the cells did something else, right? There are population effects there, right? So the question then is, how can we take the knowledge that is acquired through the reductionist experiments that we actually do, and scale that up to the level of organs, tissues, and patients, right? And that's what the translational systems biology is intended to do. Now, a regular, biomedical researcher, they intuit what those leaps are. And again, what we're trying to do is we're saying, just show us what you've done, right? Give me something tangible so I can play with what your intuition is, what your hypotheses are, and are able to probe it. Because in the absence of that type of visualization, so let me go back to the show your work for the math problem sort of thing. If you don't show your work and you get the wrong answer, you don't know what you did wrong, right? So for this cycle of falsification in science to function appropriately, your failures need to be useful. You can't go back to square one and have to reconstitute the whole thing again, right? So to a certain degree, what we want is we want to inject the concept of useful failure into the hypothesis testing scientific cycle. So if something doesn't work, we can go back and say, okay, it didn't work because of this, or it didn't work because of that, right? And that's how you can actually move forward, instead of having to reboot everything and then try all of it again.
Yeah, so what goes hand in hand with that is that these are basically engineering principles. So just like we didn't invent the computational modeling tools that we use, although we definitely created some variants of them, we didn't invent this way of thinking. It's an engineered system. So I asked before if anybody was in the biomedical research field. So let me ask you another question that hopefully everybody can raise their hands for. Who here has ever interacted with an engineered system? Like, have you ever been on an airplane? Anybody want to? I don't know. Maybe nobody here flies. I could be that everybody's Amish.
Driven in a car.
Driven a car.
Used a computer.
Okay. So if you probably think, wow, I've got this nice new car. It's got all of these besides anti-lock brakes, lane avoidance, and automatic rain sensing wipers, and you know that there's gigabytes worth of processing going on in a car right now, and so you must think, I bet you those computer models or code that's running in the back must be really complicated, right? Like we heard about the Toyota brake system failure, and then they were blaming software, so it's got to be complicated. But when you talk to the engineers that build these things, and hopefully this won't stop you from getting on an airplane, but the actual models that they do are abstracted enough, and the degree of complexity of the models is actually much less than you'd believe. Which means that we trust our lives every day, wherever we are. You're flying out tomorrow, I'm flying out Tuesday. So we trust our lives, we trust our families' lives on these devices that are technological and electronic, and they look cool. And we think that underneath it all is some engineering that's got to be incredibly complicated. But actually, it's much less so for the amount of stuff these things actually do. Which means there's a ton of abstraction going on, right? And so to take a society that says, for being on an airplane and driving a car and putting a space shuttle up in the air, I'm willing to have models that are less than perfect. Oh, but for your biomedical problem, we need to know every gene. Really? I mean, to cure someone, we need to know every gene. People have been curing people before they knew everything about their gene. People have been curing people since prehistory.
Aspirin's a great drug. When it came about, nobody knew how it worked.
Right. So
it does a whole bunch of stuff.
So it becomes a very strange kind of rationale that people are giving. Now, when you say, well, in order to really, really understand biology, we really need this. I'm not saying that we don't. It'll be definitely very nice. But in order to have actionable knowledge, it's not that we need 1,000 more molecules. We need to take the molecules we have and put them in the right context with the right level of abstraction, which is what engineers have done always, right? It's what we trust engineers to do now. It's not any brand new science. It's not any brand new idea, right? So if you take all these pieces together, as much as I've just told you, I've just discredited our credibility of like, why is this new? But the bottom line is, it's new because no one else is doing this. No one else is thinking this. No one else is putting these dots together in this way. Because the as Gary was saying, the alignment of incentives, the kind of tail wagging the dog effect, have led to a very, very strange situation, as we read in that initial passage, which is we know more and more. But the question is, why are we knowing more and more? Are we knowing more and more because without knowing more and more we can't do actionable stuff? I would argue not. I would argue we know more and more because we want to know more and more, or because some people want to know more and more, or because you can make a lot of money from technology that lets you know more and more. And some of it turns out to be really useful. But it's not because without it, we can't make the next logical leap.
So we talk a little bit about this in the book with respect to the intellectual legacy of biology. Right? So if you look at biology prior to the 1920s, 30s, and 40s, it's basically making lists of descriptors, right, of things. Right? Biologists were zoologists and botanists, right? And the great advances in biology were basically descriptive, right? And the concept of process didn't actually come in until Darwin started talking about evolution and Mendel started talking about genes. So Heisenberg gave a series of lectures in the 20s called What is Life? Looking at whether or not there are is there a way to link chemistry and physics to biological processes, right? Because we don't want vitalism anymore, more biology is physical systems, right? There must be some underlying mechanisms involved. And that basically showed in the molecular biology revolution. Now you would think that this concept of dynamics from the physics background would also percolate through. But this biological legacy is that we just make increasingly larger lists of descriptions of things. Right? So that's what the Human Genome Project is. It's a list of all the genes that people have. This is what GWAS is. It's a list of all the genes that you happen to have. Right? These are what omics are. This is what big data is. We're constructing larger and larger lists in which to characterize the systems that we have. What we actually want to know is how does one set of descriptors translate to that same organism but a different configuration an hour later or 2 hours later, etc. That requires the abstraction away from the list acquisition. That is the biological legacy.
I mean, to use another analogy, imagine like if I had a bolt of cloth, right? I've just got a bolt of really nice wood cloth and I lie it down here and I go, how's this going to look as a suit? Most of you could go, okay, well, I mean, I kind of know what a suit looks like and whatever, but I mean, I can't quite go from that cloth to the suit. And if I said, well, let me put a mannequin up here and then we can drape it around and it'll probably help you, right? So you put a structure on it. So the analogy to this problem is, I went to that same bolt of cloth, and instead of giving you a mannequin to hang it on, I said, let's make the bolt of cloth twice as big. Is that going to help you? If I said, if I said 1 plus 1 equals 3, you go, that's wrong. Okay, no, 1 plus 1 equals 3.0000005. Am I any more correct? No, but I stuck a whole bunch of decimals at the end of it. I'm much more accurate. I've measured more stuff. I'm still completely wrong.
So we started this book focusing on inflammation because that's what our actual research areas are. But as we delved into the fundamental problems associated with the research process, it became evident that what we were dealing with is actually a basic fundamental scientific problem. To a certain degree related to certain imbalances in the advances of various technologies, but also having to do with the social, political, financial, regulatory system that governs biomedical research and manages academic science as well. And these sorts of issues, as we looked into them, seem to have more basic fundamental concepts that need to be revisited. So for instance, if you look at this wall of philosophy on the left here, right, there's a whole bunch of very, very brilliant people who have written extensively about the nature of knowledge, experience, and how we know what we know, and how do we increase our knowledge, and how do we turn that into something that allows us to interact with the visible world. Right? We can't ignore those particular processes just because we have a new assay, or just because we find a new molecule. right? We need to contextualize the knowledge that we generate and look to our intellectual traditions with respect to science to see whether or not this paradox that we find ourselves in is actually intractable, or are there lessons from that very rich intellectual history that we can use to allow us to bootstrap beyond what appears to be a current ledge that we're stuck on. So this book that we wrote goes into those sorts of issues, dealing with the philosophical basis of science, epistemology, the scientific method, how that's become implemented, the history of biological investigation, the benefits and the consequences of the molecular biology revolution, issues with respect to complexity science, and the current academic environment that we currently have. And I think that a lot of these issues have kind of coalesced in a very negative sense that appears to provide barriers to us actually finding tractable solutions to what we actually want to do, which is just take care of people. Right? We want to be able to fix people from the diseases that they have. Right? So that's the impetus for this. I'll let Yoram expound a little bit more.
Let me just first ask, how many people in the room are involved in any way in biomedical research, either doing it, thinking about it? All right, you'll be arrested, right? Right? Yeah. So okay. So I was actually wondering if there'd be any students that might be just thinking about going towards
Mine
that
is
field.
by induction.
Okay.
Though I did think about these things 30 years ago.
Okay. Well, that's actually not a bad idea because you probably skipped some of the period where many of the problems we talk about was generated. So let me just ask you a question. So how many of you would just characterize the science, especially biology and related sciences, as being, very rational, very mechanistic, very objective? Most of you. Is that reasonable? I mean, I'm just interested in seeing what you think. If you're not raising your hand, what do you think biology is like right now, from just your knowledge of it, from the press or from what things you read? Anybody want to be brave and say something? No?
I mean, I can
Okay.
venture because my son is in systems biology. So
All right. Well, even
So
perfect.
I can
Great.
venture.
So you know the answer.
The old world biology was more a collection of facts and of processes and of chemistry and that kind of stuff.
Okay.
And but the cell behavior itself and how cells begin to deviate and begin to become what they become, in effect requires information, and therefore you need a lot of computation to figure out cause-effect relationships.
Okay.
So in that sense, your field of computational biology and looking at combinations of genes and what kinds of mathematical spaces you can get in order to figure out syndromes and then figure out what is the cause, that kind of stuff
Right.
is where I think your field is today in some areas.
Well, that's what I say. So
Yeah.
you think the field is in this space right now? Do you think in general, if you had to say, I have to give a characterization to where biomedical research is, your experience through your own son, you think that that's kind of where things are right now? Or do
No,
you think,
they're not. I mean, they're
being in this place,
Yeah.
in the pinnacle of science,
Yeah.
do you think that that's where it is?
No, it's in
across-
its infancy. They're taking very, very basic baby steps. And since I live close to NIH and I have links there, if you listen to them, they are taking even more baby steps and infantile steps.
So that's exactly right. And then, in fact, I would say it's more than that. So Gary has his view of where the fundamental problem lies, and I agree with that. I think that you can think of a more rubber meets the road version of where the problem lies. So here's where the problem lies right now. Let's say I'm an eminent biomedical researcher, or at least someone who publishes as if he is. Okay. And then somebody, let's say you're another one, right? And we both have a hypothesis about the role of a molecule in some disease, okay? I have my hypothesis. It's backed by the research in my lab, and then I could give you maybe 10 papers or whatever, some number of papers that back up my opinion. And I'm sorry, I didn't get your name.
My first name is Ravi.
Okay, so Ravi is another eminent scientist, and he's got also a bunch of publications, and he's also got that his lab have put out there about a very a different role for that same molecule. Like, I really think that we should be antagonizing that molecule to make an effective drug. He thinks it's the last thing you should do, right? I can show you my research that backs up my opinion. He can get up in the same conference and show me his research that says that backs up his point of view, and he can show me 10 papers from other people that back up his point of view, right? So which one of us is right? You don't know. No, well, so, right, so one possibility is it's both, another possibility is it's neither, right? Another possibility is that the molecule has, you know, who knows what it has or doesn't have to do. The bottom line is, okay, who's going to decide? Who is going to be the arbiter of which one of us is right? No one. There is no authority to do that. There's just the process of debate and discussion, and then maybe politics, and then maybe which one of us can get a grant funded that allows us to get our work done more than the other, and which one outpublishes the other, and which one of us gets papers into better journals. But there is not any place that definitively says, this idea is right, that idea is wrong, or neither idea is right. Right? That is actually the state of biomedical research right now. And you might say, well, that's just how it is. I mean, you know, you take a chance on life every time you walk out of the street, right? And so science should be the same way. Who knows who's right? Who knows what's going to work? So the point of this book is that computational technology, I'm not even going to say has advanced to the level that can allow you to create models that could, in fact, show you this. Our argument is that some of this computational technology existed 30 to 50 years ago, that it was not really ever leveraged in the way that it could have been. The thought process behind how to put together the pieces into a mathematical model or some other similar structure that basically says, hey, look, every piece you guys argue about, here it is, and when you put it all together, it is either option A or option B or some new option C that neither of us supports. The fact is that that technology exists. That is what we based our careers on. We've been doing it for 15 years, and we didn't invent much of it, right? We used technology that was available. So the piece that wasn't available was the desire to go down that route. Because most people find it much easier to espouse their favorite point of view, which in theory is a hypothesis, but in fact is more of a statement of, you know, what you believe so strongly about that it becomes close to sometimes a religious, you know, circle. So maybe Gary, you can talk about the whole hypothesis.
So this is how we got back to the fundamentals of science, which is observation, hypothesis generation, and then hypothesis testing. And I think the thing that is immediately evident if you delve into biomedical research is that there is no capital T truth, right? We don't actually know. Now, there's a great deal of incentive in the biomedical community to try and erase doubt, right? Because we want to make people feel comfortable, right? That we know what we're doing. And it is a little disconcerting when you hear that, well, we actually don't know that very much for sure. Now, a observant observer is going to say, well, you said something different 10 years ago, and now we're doing something different. How can that be? Right? So to a certain degree, this is a problem with how the scientific community conveys scientific output to the general community, right? By giving it a quote-unquote objective capital T truth, this is how the way things actually are. As opposed to, this is our best approximation of how things actually work. Right? So the idea then is that as you go through science, you do the scientific process from Newton and Francis Bacon, is that you're constantly trying to falsify the hypotheses that you come up with. Right? So this is the skepticism that should be fundamental to the scientific process. Right? Because we're always looking to potentially disprove what we believe, and our failure to disprove what we believe makes us have a little bit more trust next time around. Now, and that's how science progresses, right? That's how we learn more things. We break the hypotheses that we come up with, and we come up with new hypotheses that have greater explanatory power. Now, if you were a physicist, you would say, I'm going to keep breaking down to quantum mechanics, and then gets me closer towards capital T truth. And then I can't disagree with that because I'm not a physicist, and I kind of believe those guys. Now, from a biology standpoint, if we want to have to know every single thing about a system to be able to use that knowledge and control that system, well, that's not good for me as a physician, because then I have to wait too long, right? I'm never going to be able to have actionable knowledge while everyone's trying to find out every single little thing about that particular system. What I want is I want to be able to have means of characterizing biological systems that have sufficient trust for me to engineer a way to control that system, right? Because I want a therapeutic. I want something that I can do for you to make you better whenever it's making you sick, right? So basic research, looking for fundamental laws and that kind of stuff, more power to it. That should be done, absolutely yes. But there's this middle ground of finding sufficient applied knowledge for us to be able to determine, well, how can we make people better in the meantime, right? We know it's not perfect, but we just need to be a little bit better, right, than what we were doing before. So skepticism is inherent to that particular process. I mean, we're taught that at the beginning, right? When we go to science class, that's the first thing we're taught about. But this issue that Yoram's talking about with respect to what the current academic and funding climate is given the fact that it's all driven by money, and the money is a zero-sum game, right? In order to be successful in that particular environment, we now need to become advocates for our hypotheses, right? Now that you're advocates for your hypotheses, you can't acknowledge the skeptical component, even for the best intended researcher. Right, the fundamental nature of their professional survival changes what their mindset is. Because now they're pushing, this is my idea, I need to get funded, this is what I do. Right, this is right, this is what's going to work. Right, now, back in your mind, you can say, yeah, maybe I can, that's not exactly right, etc., etc. But when you're presenting that as a grant, you can't really show those cracks, or else you're going to get stomped. So I think one of the things that became evident when we were working on this book is the idea to use computational models to accelerate this process of hypothesis falsification, right? This is the concept of in silico science, right? So we're taking essentially a page from Einstein's thought experiment book, right? Where what we want to be able to do is to take the process by which a good biomedical researcher already does, which is they look at a system, they come up with a conceptual model, they run it through their minds and figure out how is this going to act, and then they design experiments with them. What we're doing is we're saying, like I tell my daughter in school in math, show your work. Right? This is what you believe, write it down. Put it in code. Give me that code, let me see how it works. Right? Because that allows us to be able to visualize and instantiate our thought experiments before we kill rats, grow cells, or actually intervene on patients. So the premise of translational systems biology is to utilize computational modeling to visualize our hypotheses and basically create this in silico sandbox that allows us to explore different configurations, different ideas, crazy things, and be able to see how systems might behave given whatever our belief system happens to be, right? Because electrons are cheaper than cells and rats, and